Let's talk about some differences between solids, liquids, and gases. So hopefully we're all familiar with these three phases of matter, and we're going to take a closer look at the comparison between the three, and that's going to give us some understanding that we'll need in our subsequent study of fluid mechanics. So fluid mechanics, when we talk about fluids, we're talking about both liquids and gases. So these are both considered fluids. And then we have solid there on the list, just so we can compare it to liquids and gases. Okay, so let's start with a description. So we know that solids hold their shape, and there's no need for a container in that case. In comparison, a liquid takes the shape of its container and will stay in an open container. The difference between liquid and gas is that a gas will expand to fill a closed container. And we all know this from personal experience. Okay, so that is just a general description. Mobility of molecules. You can see here in the description that solids have a low mobility because they're bound by strong intermolecular forces. A liquid still has strong intermolecular forces, but they're not as strong as in a solid. Consequently, the molecules move around more freely in a liquid, and that's what gives them the properties that we know that they have. Okay, and last but not least, a gas will move around freely because their intermolecular forces are weaker. And you can see in the description that is why gases expand to fill their container. Okay, let's move on to density. As you would intuitively guess, the density of a solid is greater than the density of a liquid. That in turn is greater than the density of gas. So let me say a couple more things about density before we move on from this topic. So many of the liquids that we study in this class are going to be modeled as incompressible. So in that case, we're going to assume that the density, the symbol which we use is that Greek letter rho, is roughly going to be equal to a constant. Okay, and that's going to be true for liquids that we model. Gases, on the other hand, have densities that are dependent on other properties such as pressure and temperature. And what you need to know for now is just that, here, let me clear some space here, that the density is not a constant. Okay, and we're going to talk about how to calculate the density of what's known as an ideal gas in particular very shortly. So just hang on to that thought. Okay, so that summarizes our discussion on density. So let's just put a check mark there. Okay, molecular spacing, as you would guess, in a solid, they're very small and close together. And in a liquid, they're also small, but they're held close by intermolecular forces. And in a gas, they are far apart. All right, let's talk about effect of shear stress. So you might have heard of this in maybe statics or mechanics of materials. But just to remind you, a shear force looks like this. So if you have an element that's shaped like a square and you produce or you apply a force that looks like that on the top surface and a force that looks like that on the bottom surface, then you are applying shear stress on that element. Okay, if you do that to a solid, you might produce a little bit of deformation. So for example, if you had a square-shaped solid, after you apply the shear force, maybe it would look, here, let me see if I can draw it in dashed lines here. Something like that, depending on how malleable it happened to be. Okay, if you do the same thing to a liquid or a gas, you can see here that it produces flow. So it's going to deform continuously under the application of shear stress, and that's going to result in flow. Okay, so just remember that fluids deform continuously under shear stress. Okay, so hopefully that discussion is clear. All right, let's move on to normal stress. So hopefully you remember from a previous class that normal stress is when you apply a force in that direction or in the opposite direction, which is called tension. So it can be in compression or tension. So you can see that for a solid, if you apply that kind of stress, then you can produce a deformation that may associate with volume change, and also you can result in failure of your solid. For a liquid and for a gas, you can see that normal stress produces deformation associated with volume change. Okay, going down the list, viscosity. So we're going to talk more in depth about the viscosity property in the next chapter, but this is just an introduction here in chapter 1. So viscosity is a measure of fluid's thickness. Here, write it like that. Okay, and as you can imagine for a solid, this is not applicable. For a liquid, you can see that the viscosity tends to be high. So liquids are considered to be thicker than gases, and you can see under the description for gas that the viscosity is going to be low in that case. Okay, let's see. The viscosity of a liquid decreases as the temperature increases. And if you think of a very viscous liquid, like let's say engine oil or maybe honey or something like that, you can see intuitively how this would be true. So basically, if you heat those liquids, they end up getting thinner and runnier, and consequently their viscosity goes down. Okay, so that is how viscosity behaves for liquids. You can see here for gases that it behaves in the opposite direction. So basically, the viscosity increases as temperature increases for a gas. Okay, you can think about that the next time you're speeding down the highway in your car. So the air flowing over your car produces a drag force, and that drag force is related to the viscosity, as we'll see later. Anyway, if it's a really, really hot day, that air is actually more viscous than if it's a really, really cold day, because of the fact that air is a gas. Okay, so just keep that in mind when you think about viscosity of a liquid. Okay, and last but not least, we have compressibility. We're not going to talk too much about the bulk modulus in this particular class, but you can go ahead and read those at your convenience and see how they compare between solids, liquids, and gases. Okay, let me just briefly address the continuum assumption, and then we'll move on to our first quiz. So the continuum assumption is one that we'll employ in this class, and it has to do with how we model fluids and how we model their properties. You can read the description in the textbook about the continuum assumption, but basically all it's saying is this, that you have to have enough molecules of whatever you're studying to have a continuous value of all fluid properties inside of there. Okay, and you can see a graph of that representation here in part B over here. Okay, you can imagine if you make your volume too small, you might just have like 1 or 2 molecules in there, and that if you were to calculate something like density, which is a property that you see over here, or you know, measure the pressure or something like that, it won't be representative of the fluid inside of this container that you see in part A over here. Okay, but if your container is big enough, then the property can be averaged within this volume. And that's going to be consistent with, let's say, the property over here, and so on and so forth. Okay. Basically, all the applications that we study in this class will invoke the continuum assumption. If you look at the analysis in the text, it says that you need, if you're looking at liquid water around room conditions, here, let me just jot it down here at the bottom. The length scale of your container has to be greater than 3.1 times 10 to the minus 6 meters. Okay, so that's pretty small, 3 micrometers or 3 microns. Basically everything that we study in this class is going to be bigger than that. Okay, if you're talking about air, which is also very common to many engineering applications, the length scale of your container has to be bigger than about 3.5 times 10 to the minus 5th meters. Okay, so again, that's about 35 microns, still really, really small. So everything that we study in this class, again, with air, would probably fall under this domain. The only time you might have to pay special attention is if you're doing some analysis maybe at the micro or even the nanoscale. Then you can see that this assumption might not be met. Okay? Or if you're doing an aerospace application maybe very, very high up in the atmosphere, then again, the molecules might be so far apart that we would not satisfy the continuum assumption. But basically speaking, for most of the applications that we do in this class, it's going to be valid.